Is there another version of you reading these exact words at this exact moment, somewhere far beyond the reach of any telescope? Not a metaphor, not a thought experiment for entertainment, but a physical person made of the same atoms, arranged in the same pattern, living a life identical to yours down to the smallest detail. A growing number of physicists take this possibility seriously. They do not arrive at it through speculation alone. They arrive at it through measurements, through the geometry of space, and through what happens when you combine an unbounded universe with a finite number of ways to arrange matter. The idea sounds impossible until you examine the reasoning behind it. Modern cosmology has uncovered evidence that the universe extends far beyond the small portion we can observe. It may extend without limit, and if space truly goes on forever, while the building blocks of reality can only be combined in so many configurations, then repetition is not a strange exception. It becomes a mathematical certainty. This is not the only path that leads to copies. The theory describing the first instant of cosmic history points toward an endless production of separate regions. The equations of quantum mechanics suggest reality may split into branches with every event. Some theorists even propose that every possible universe consistent with mathematics genuinely exists. These are distinct ideas built on different foundations, yet they converge on the same unsettling conclusion. You may not be alone. You may be one of countless identical beings spread across a reality far larger and stranger than human intuition was ever designed to grasp. The question is how seriously the science supports this and where the evidence runs out. To understand why serious scientists entertain the idea of cosmic copies, we have to begin with a question that sounds almost childish in its simplicity. How big is the universe? Most people carry an intuition that the universe is enormous, but ultimately a single thing, a vast container holding all the galaxies and stars and empty space that exist. That intuition feels reasonable. It is also almost certainly incomplete, and the reasons why force us into territory that overturns ordinary assumptions about distance, observation, and the limits of what we can ever know. The first thing to confront is that the universe we see is not the universe that exists. When you look up at the night sky, you are not seeing things as they are now. You are seeing light that left its source long ago. The light from the sun takes about 8 minutes to reach us, which means we always see the sun as it was 8 minutes in the past. The nearest star beyond the sun lies so far away that its light spends several years crossing the gap. Look deeper into space, and you look deeper into time. The most distant galaxies we can detect appear as they were when the universe was young, because their light has been traveling toward us for nearly the entire history of the cosmos. This is not a limitation of our instruments. It is built into the structure of reality. Light moves at a fixed speed, and that speed, while astonishingly fast by human standards, is finite. Information cannot reach us faster than light can carry it. This finite speed, combined with the finite age of the universe, produces a profound consequence. There's a maximum distance from which light has had time to reach us since the universe began. Light from anything farther away simply has not arrived yet. It may be traveling toward us right now, but it has not completed the journey. This boundary is called the cosmic horizon, and it defines what we call the observable universe. Everything within that horizon is, in principle, visible to us. Everything beyond it is hidden, not because it is dark or obscured, but because no signal from it has had the time to cross the intervening space. It helps to think about this using a familiar example. Imagine standing in the middle of a calm ocean at night. You can see only so far before the curve of the Earth hides everything beyond. That visible circle is your horizon. Ships beyond it are not gone. They are simply out of sight. If you climbed higher, your horizon would expand and you would see farther. The cosmic horizon works on a similar principle, except that climbing higher is not an option. The horizon is set by the speed of light and the time available, and we cannot exceed either. As the universe ages, the horizon slowly grows, because light from ever more distant regions gradually finds time to reach us. But at any given moment, there's a hard edge to our knowledge, a sphere of visibility surrounding us in every direction. Here is where intuition begins to fail. People often assume that this horizon marks the edge of the universe itself, as if beyond it there is nothing. That assumption has no basis. The horizon is not a property of the universe. It is a property of our position and our moment in time. An observer in a galaxy billions of light years away would have their own horizon centered on themselves, encompassing regions we cannot see and excluding parts of what we can. There is nothing special about our location. We sit at the center of our observable universe for the same reason a sailor sits at the center of their visible ocean. The horizon follows the observer. It tells us about the limits of observation, not about the limits of existence. So the observable universe is a sphere, and we are at its center, and its radius is determined by how far light has traveled since the beginning. That radius is larger than the simple age of the universe might suggest, because space itself has been expanding while the light traveled. The expansion stretches the distances, carrying distant regions farther away, even as their ancient light crawls toward us. When astronomers account for this stretching, they find that the edge of the observable universe currently lies an enormous distance away, far greater than the distance light could cover in a static, unchanging space. The numbers involved strain comprehension, but the principle is straightforward. We see a finite bubble of space, and that bubble is vast, and it is only a portion of something larger. The crucial question then becomes, how much larger? And this is where measurement enters, transforming the discussion from philosophy into science. To estimate the true extent of the universe beyond our horizon, cosmologists study the overall shape of space. This is not as abstract as it sounds. Space has a geometry, and that geometry can be measured. The geometry tells us whether space curves back on itself, like the surface of a sphere, or curves away from itself, like a saddle, or remains flat, like an unbounded sheet extending in every direction. Each of these possibilities carries different implications for the size of the universe. A space that curves back on itself could be finite, wrapping around so that traveling far enough in one direction eventually returns you to your starting point. A flat or saddle-shaped space, by contrast, could extend without limit. How does one measure the shape of something as large as the universe? The method relies on light from the early cosmos, a faint glow that fills all of space and carries information from a time shortly after the beginning. This glow contains patterns, slight variations in temperature from one region to another, and the apparent size of those patterns depends on the geometry of the space the light has traveled through. If space were curved, the patterns would appear distorted in a predictable way, either magnified or shrunk depending on the direction of the curvature. By comparing the observed size of these patterns with the size they should have if space were flat, scientists can determine the geometry with remarkable precision. The results have been consistent and striking. Within the limits of measurement, space appears to be flat, not approximately flat in a casual sense, but flat to a high degree of accuracy, with any curvature falling below the threshold our instruments can detect. This finding has deep consequences. A flat universe does not curve back on itself. It does not wrap around. As far as the geometry can tell us, it extends outward in every direction, and there is no observation suggesting it ever stops. Of course, flatness within our measurements does not prove infinity. A space could be very slightly curved in a way too subtle to detect, and a slight curvature could still permit an eventual edge or a wrapping around at scales far beyond our horizon. Science is careful here. The measurements tell us that if the universe is finite, it must be enormously larger than the part we can see, large enough that its curvature hides below our detection limit. The flatter the measured geometry, the larger the minimum possible size of the total universe. Some estimates, based on how flat the universe appears, suggest that the full extent of space must be at least hundreds of times larger than the observable region, and possibly far more. The true universe could be larger than our visible bubble by a factor so immense that the observable universe becomes a single grain in a desert of unimaginable scale. And there remains the genuine possibility, fully consistent with everything we have measured, that space simply has no end. that it extends infinitely in all directions, containing an unlimited volume, an unlimited number of galaxies, an unlimited quantity of matter. This is not a fringe idea. It sits comfortably within mainstream cosmology as one of the live possibilities the data permits. The measurements cannot confirm infinity, because no measurement could ever survey an infinite space. But they are entirely compatible with it, and many of the leading theories of cosmic origins actively predict it. This is the foundation on which the idea of copies rests. We have established that what we see is a finite sphere bounded by the speed of light and the age of the universe. We have established that this sphere is not the edge of anything real, but merely the edge of our vision. And we have established, through direct measurement of the geometry of space, that the universe beyond our horizon is vastly larger than the part we observe, perhaps without any limit at all. Each of these conclusions follows from evidence, not from imagination. They are the careful, measured results of observation and theory working together. But notice what we have not yet done. We have described a universe that may be infinite in extent, filled with matter, governed by physical laws. We have not yet asked what an infinite expanse of matter actually implies. We have not asked what happens when you take an unbounded space and fill it with particles that can only combine in a limited number of ways. The geometry has opened a door. What lies on the other side depends on a different kind of reasoning, one that moves from the shape of space to the arrangements of matter within it. And that reasoning leads somewhere the geometry alone could never take us. If space is truly endless, then how many different things can it actually contain? The leap from an infinite universe to infinite copies of yourself depends on a single, subtle idea that most people never stop to consider. It is the idea that there is a limit to how many different ways matter can be arranged within any given region of space. This sounds counterintuitive at first. We are used to thinking of variety as endless. A child with a box of building blocks can seemingly construct an unlimited number of shapes. A painter with a palette can create scenes no one has ever imagined. The world feels inexhaustibly diverse. Yet beneath that apparent boundlessness lies a hard mathematical truth. And once you grasp it, the conclusion about copies becomes almost impossible to escape. Consider a finite region of space, say a volume the size of a single room. Now ask how many physically distinct arrangements of matter that room could contain. The room holds a certain number of particles, and those particles can occupy different positions, move with different velocities, and combine into different structures. At first, this seems to allow infinite variety. You could shift a single atom by a hair's width and call it a new arrangement, and you could keep shifting it forever in ever smaller increments. If that were true, the number of possible arrangements would indeed be infinite, and the argument for copies would collapse before it began. But physics tells us that this infinite refinement is an illusion. Reality at its deepest level is not smooth, it is grainy. The behavior of matter at the smallest scales is governed by quantum mechanics, and quantum mechanics imposes limits on how finely we can distinguish one state from another. There is a smallest meaningful unit of position, a smallest meaningful difference in energy, below which the distinction between two configurations ceases to have physical meaning. You cannot shift an atom by an arbitrarily tiny amount and produce a genuinely different state. Below a certain threshold, the two arrangements are not two things, they are the same thing. This graininess means that within a finite volume containing a finite amount of energy, the number of truly distinct arrangements is not infinite. It is enormous beyond comprehension, but it is finite. An analogy helps make this concrete. Think of a digital photograph. From a distance, it looks perfectly smooth, capturing infinite gradations of color and shade. But zoom in far enough and you discover that the image is made of pixels, each pixel a single block of one specific color drawn from a fixed palette. The number of possible images that a screen of a given size can display is large, almost incomprehensibly large, but it is not infinite. There are only so many pixels, and each pixel can take only so many colors. Multiply the possibilities together, and you get a vast but finite number of distinct images. Every photograph that has ever been taken, and every photograph that ever could be taken at that resolution, is somewhere in that finite set. The universe, at the smallest scale, behaves more like the pixelated screen than like the smooth image we perceive. Space and energy come in finite countable units, and a finite region can hold only a finite number of distinct configurations. Now, hold that idea steady and combine it with what we established about the size of the universe. We have a space that may extend infinitely, filled everywhere with matter under the same physical laws. And we have the principle that any finite region can exist in only a finite number of distinct states. Watch what happens when these two facts collide. Imagine dividing the infinite universe into regions, each the size of our observable universe, each a sphere bounded by the same horizon distance that limits our own vision. In an infinite universe, there would be an infinite number of such regions, stretching on without end in every direction. But each region, being finite in size and energy, can exist in only a finite number of distinct arrangements of matter. The conclusion is forced upon us by simple counting. If you have an infinite number of regions, and each region can take only a finite number of possible forms, then some forms must repeat. They must repeat not occasionally, but infinitely often. There is no way to distribute an infinite number of items among a finite number of categories without filling some categories an infinite number of times. This is not a quirk of cosmology. It is a basic feature of how infinity interacts with finiteness. Picture dealing cards from a deck that never runs out. There are only 52 distinct cards, but if you deal forever, every card appears again and again without limit. The finiteness of the deck guarantees repetition when the dealing is infinite. The universe, in this picture, is dealing regions of space, and the deck of possible arrangements, while vastly larger than 52, is still finite. Infinite dealing from a finite deck produces infinite repetition. This means that somewhere, in the unbounded reaches of space, there must exist a region identical to our own observable universe. Not similar. Identical. Every galaxy in the same place, every star burning the same fuel, every planet following the same orbit. And on one of those planets, in a setting indistinguishable from your surroundings right now, a person identical to you in every physical particular. The same arrangement of atoms in the same brain, holding the same memories, reading the same words at the same moment. This is not a poetic flourish. It is the direct logical consequence of two well-supported premises. If space is infinite, and if a finite region admits only finitely many states, then copies must exist, and they must exist in infinite number. The instinctive response is to resist. Surely something this strange cannot follow from such ordinary reasoning. But the strength of the argument lies precisely in how ordinary each step is. There is no exotic mechanism invoked, no untested theory, no appeal to mystery. There is only the geometry of space, which measurement suggests is flat and possibly infinite, and the graininess of matter, which quantum physics establishes with great confidence. The conclusion is uncomfortable, but the premises are mundane, and the logic connecting them is airtight. To reject the conclusion, you must reject one of the premises, and rejecting them is harder than it looks. We can even reason about how far away the nearest copy might lie, at least in principle. The calculation runs as follows. Count the number of distinct possible arrangements for a region the size of our observable universe. That number is staggering, written as the figure 2 raised to an exponent so large it dwarfs the number of particles in everything we can see. Now, imagine traveling outward through an infinite universe, passing region after region. On average, you would need to pass through roughly that many regions before encountering one identical to your starting point. The distance involved is so vast that no human language has a natural way to express it, and no journey could ever traverse it. The nearest exact copy of you might lie at a distance measured in numbers that exhaust the ordinary vocabulary of scale. Yet, finite or not, the distance exists, and beyond it, the copy exists too, along with infinitely many others scattered through the endless expanse. It is worth pausing on what kind of claim this is. It is not a claim that we can verify by observation, because the copies lie far beyond any horizon we could ever reach. Light from them will never arrive. We cannot photograph them, signal them, or detect them in any way. In that sense, the claim sits at the boundary of science, derived from scientific premises, yet pointing toward conclusions that observation can never confirm. Some scientists find this troubling and argue that a claim which cannot be tested has stepped outside the proper domain of science. Others reply that the premises themselves are testable, that we can measure the flatness of space and confirm the graininess of matter, and that if those premises hold, the conclusion follows whether or not we can travel far enough to witness it. The disagreement is genuine and unresolved, and it marks one of the places where cosmology brushes against the limits of what science can claim to know. There is also a more subtle point hidden in the reasoning, one that sharpens the strangeness rather than softening it. The argument does not merely predict a single distant copy. It predicts a graded spectrum of near copies and exact copies and everything in between. Closer than the nearest perfect duplicate, there would be regions almost identical to ours, differing in some small detail, a single misplaced atom, a slightly different cloud formation over a distant city, a conversation that went one word differently. Closer still, there would be regions matching ours in their broad features, but diverging in their histories. The infinite universe, in this picture, contains not just one alternate version of your life, but a continuous range of them. Near misses and distant variations and perfect repetitions, all coexisting in the same physical reality, separated only by distances too great to cross. This vision rests entirely on the assumption that space is genuinely infinite, or at least large enough to contain the necessary number of regions. If space turned out to be finite and not too large, the whole argument would dissolve, because a finite universe might not contain enough regions to guarantee even a single repetition. So everything hinges on the true size of the cosmos, the very question we examine through the geometry of space. The measurements lean toward flatness, and flatness leans toward vastness, and vastness taken to its limit delivers the copies. But measurements have uncertainty, and flatness is not quite the same as infinity, and the argument, for all its logical force, stands on a foundation that observation has not fully secured. And yet this is only the first of several roads that lead to a multitude of universes. The reasoning we have followed depends on space being infinite within a single universe governed by uniform laws. But there is another idea, arising not from the size of space, but from the violent events of cosmic birth, that points toward an entirely different and perhaps even larger collection of worlds. It begins with a question about the first fraction of a second after the beginning, and about a process so explosive that it may have created not one universe, but an unending cascade of them. What happened in that first instant, and why might it never have truly ended? The story of cosmic creation that emerges from modern physics does not begin with a gentle unfolding. It begins with an episode of expansion so rapid and so extreme that it strains the imagination, an event that lasted a fraction of a second, yet shaped everything that followed. This event is called inflation, and it was proposed not to explain copies of universes, but to solve a set of stubborn puzzles about why our cosmos looks the way it does. To understand how inflation leads to a multitude of worlds, we first have to understand the problems it was invented to solve, because the solution carries consequences far beyond the questions that prompted it. The first puzzle concerns the remarkable uniformity of the universe on large scales. When astronomers measure the faint glow left over from the early cosmos, the radiation that fills all of space and carries the imprint of conditions shortly after the beginning, they find that it has almost exactly the same temperature in every direction. Point your instrument at one patch of sky and measure the temperature of that ancient light. Point it at the opposite patch in the completely opposite direction, and you measure the same temperature to extraordinary precision. This seems unremarkable until you consider what it implies. Those two patches of sky lie on opposite sides of the observable universe. Light from one could never have reached the other, because there has not been enough time since the beginning for any signal to cross that distance. They have never been in contact. Nothing has ever passed between them. And yet they share the same temperature, as if they had somehow coordinated, as if they had reached a common equilibrium despite never having interacted. This is genuinely strange. Imagine arriving at a party and finding that every guest, none of whom had ever met or communicated, had independently chosen to wear exactly the same shade of clothing. You would suspect some hidden coordination, some shared cause that you had not yet identified. The uniformity of the early universe presents the same suspicion. Regions that could never have communicated nonetheless match each other precisely. Some common cause seems to be required, some shared origin that brought these distant regions into agreement before they were separated. Without such a cause, the uniformity is an unexplained coincidence of staggering proportions. The second puzzle concerns the flatness we discussed earlier, the geometry of space that measurement finds so close to flat. It turns out that a flat geometry is not a natural resting state for a universe. According to the equations governing cosmic expansion, any small departure from perfect flatness in the early universe would grow over time, amplified by the expansion until the curvature became obvious. For the universe to appear flat today, after billions of years of expansion, it must have been flat to an almost inconceivable degree at the very beginning. The slightest curvature at the start would have ballooned into a dramatic curvature by now. The fact that we observe near perfect flatness means the universe began in a state of fantastically precise flatness, balanced on a knife's edge. Why would it begin in such a special, finely tuned condition? Without an explanation, this too looks like an extraordinary coincidence, a universe that happened to start in exactly the rare state needed to appear flat eons later. Inflation addresses both puzzles with a single bold idea. Suppose that in the first tiny fraction of a second, the universe underwent a brief period of expansion at a rate vastly exceeding anything seen since. Not the gradual expansion we observe today, but an explosive, accelerating growth that doubled the size of space again and again in almost no time at all. In this picture, a region far smaller than a single particle would have ballooned in an instant to a size larger than the entire observable universe. The numbers involved are extreme. Space expanded by a factor so large that a region of subatomic dimensions grew to cosmic proportions before the first fraction of a second had elapsed. This single proposal resolves both puzzles at once. The uniformity is explained because the entire observable universe originated from a tiny patch that was small enough, before inflation, for its parts to be in contact and reach a common temperature. Inflation then stretched that uniform patch to enormous size, carrying the uniformity along with it. The patches of sky that seem never to have communicated were in fact in contact long ago, when they were packed together in the tiny pre-inflationary region. Inflation pushed them apart faster than light could keep up, separating them so completely that they now seem to have no shared history, even though they began as neighbors. The flatness is explained by the same stretching. Whatever curvature the universe had before inflation, the enormous expansion flattened it, just as the surface of a balloon appears flatter and flatter as you inflate it to greater size. Stand on a small balloon and the curvature is obvious. Inflate it to the size of a planet and the surface beneath your feet looks flat. Inflation took whatever curved geometry existed and stretched it so dramatically that the result is indistinguishable from flat. The elegance of this solution is part of why inflation has become a central pillar of modern cosmology. One idea, a brief burst of extreme expansion, dissolves two separate mysteries and does so cleanly. And inflation makes further predictions that observation has confirmed. The tiny variations in temperature across the ancient light, the slight differences from one patch to another that ride atop the overall uniformity, match the pattern that inflation predicts. These variations are thought to arise from quantum fluctuations, the unavoidable jitter of matter and energy at the smallest scales, which inflation stretched to cosmic dimensions. Those stretched fluctuations became the seeds of structure, the slight overdensities that gravity later pulled together into galaxies and clusters. The detailed statistics of these temperature variations, measured with great care, agree with what inflation predicts. This is significant. A theory invented to solve two puzzles turned out to predict a third independent feature of the universe, and that feature was found exactly as predicted. Such success lends inflation considerable credibility. But inflation, once accepted, carries an implication that its inventors did not initially anticipate, and this implication is what leads us toward a multitude of universes. The question is, what drives inflation, and more importantly, what stops it? Inflation is thought to be powered by a peculiar form of energy, a field-filling space that behaves in an unusual way, pushing space to expand rather than pulling it together. As long as this field maintains a certain value, inflation continues, doubling space again and again. Inflation ends in a given region when this field decays, releasing its energy and converting it into the hot, dense soup of particles that eventually cooled into the matter we see. The end of inflation in our region is what we might think of as the beginning of the ordinary universe, the moment the explosive expansion gave way to the slower expansion and the gradual cooling that produced atoms, stars, and galaxies. Here is the crucial subtlety. The decay of the inflationary field is not a uniform, simultaneous event across all of space. It is governed by quantum mechanics, which means it is fundamentally probabilistic. In some places, the field decays sooner, ending inflation and producing a region of ordinary universe. In other places, the field happens to persist and inflation continues. Because inflation expands space so rapidly, the regions where inflation continues grow explosively, vastly outpacing the regions where it is stopped. Even as bubbles of ordinary universe form here and there, where the field has decayed, the inflating space between and around them expands so fast that it constantly creates more volume than the bubbles consume. The inflating region does not shrink as bubbles form within it. It grows and grows faster than the bubbles can fill it. This leads to a startling possibility. Inflation, once begun, may never fully end. It may end locally, in particular regions, producing isolated bubbles where ordinary universes take shape, while the larger inflating space continues expanding eternally, forever spawning new bubbles in its ever-growing volume. This idea is called eternal inflation, and it follows naturally from combining the inflationary mechanism with the probabilistic nature of the field's decay. If inflation is eternal, then our universe, the entire observable cosmos and the vastly larger region beyond our horizon, is merely one bubble among an unending and ever-increasing multitude of bubbles, each one a separate universe formed when inflation ended in that particular patch. The picture this paints is difficult to hold in the mind. Imagine a vast, eternally expanding ocean of inflating space, and within it, here and there, bubbles forming and growing. Each bubble a self-contained universe with its own history, its own galaxies, its own slow evolution from hot beginning to whatever end awaits it. Our universe is one such bubble. It formed when inflation ended in our patch billions of years ago, and it has been expanding and cooling and producing structure ever since. But beyond the edge of our bubble, the inflating ocean continues, and other bubbles form within it, and the process has no end. The ocean was perhaps always inflating, and it will inflate forever, and the number of bubbles it produces grows without limit. Notice how this differs from the picture we developed earlier. The first road to copies relied on a single infinite universe with uniform laws, in which repetition arises from the finiteness of possible arrangements. This second road, eternal inflation, gives us not one universe, but a multitude of separate universes, each one a bubble, each one potentially as large as or larger than our own observable cosmos. These bubbles are causally disconnected from one another. The inflating space between them expands so rapidly that nothing can cross from one bubble to another. They are separate worlds, isolated by an ocean of inflation that grows faster than anything could ever traverse it. Where the first road gave us copies within one universe, the second gives us a collection of universes, and within each of those, if it is large enough, the first road's logic could operate again, producing copies within each bubble. The two ideas, then, do not compete so much as compound. Eternal inflation produces an endless number of bubble universes. If any of those bubbles is itself infinite or sufficiently vast, it contains copies in the manner we already described. The result is a hierarchy of multiplicity, copies within universes and universes within an eternal inflating expanse, a structure of staggering scope arising from a theory originally meant only to explain why distant patches of sky share the same temperature. But this raises a question that the inflationary picture alone cannot answer. If our universe is one bubble among countless others, are all those bubbles the same? Do they all share the same physical laws, the same constants, the same fundamental properties? Or might the bubbles differ from one another, each forming with its own distinct character, its own version of the rules that govern matter and force? The answer to this question determines just how strange and varied this collection of universes might be. And it leads us into one of the most provocative ideas in all of theoretical physics. What if the laws of nature themselves are not fixed, but vary from one bubble to the next? The possibility that the laws of physics might differ from one universe to another represents a profound departure from how science has traditionally understood the cosmos. For centuries, the laws of nature were regarded as absolute, the same everywhere and at all times, an unchanging framework underlying all of reality. The strength of gravity, the mass of an electron, the way particles interact. These were taken to be fixed features of existence, not variables that could take different values in different places. The idea that they might vary, that another universe might operate under a different set of rules entirely, challenges this assumption at its root. Yet this is precisely what some of the most ambitious theories in modern physics suggest, and the reasoning behind it deserves careful examination. To approach this idea, we need to distinguish between two kinds of physical truth. There are the deep underlying laws, the fundamental equations that govern reality at its most basic level, and there are the particular values that appear within those laws, the specific numbers that determine how strong each force is and how heavy each particle is. The distinction matters. It is possible for the underlying laws to be universal, the same in every bubble, while the particular values that emerge within those laws differ from bubble to bubble. Think of it like a single master equation with adjustable settings. The form of the equation stays the same, but the settings, the dials that fix the strengths and masses, can be turned to different positions in different universes. The laws are shared, but their expression varies. Why would the values vary? The answer connects back to the inflationary picture and to a property of the universe that physicists call the vacuum. In everyday language, vacuum means empty space, the absence of matter. But in physics, the vacuum is not truly empty. It is a state of space itself, and that state has properties, including an energy and a set of conditions that determine how particles behave within it. Crucially, space can exist in different vacuum states, much as a substance can exist in different phases. Water can be ice, liquid, or vapor, and these are different states of the same underlying substance with dramatically different properties. The phase of the water determines how it behaves, whether it flows, holds a shape, or expands to fill a container. In a similar way, space can settle into different vacuum states, and the vacuum state determines the effective physical properties within that region, including the strengths of forces and the masses of particles. When inflation ends in a particular bubble and that bubble becomes an ordinary universe, the bubble settles into a particular vacuum state. Different bubbles might settle into different vacuum states, and if they do, they would exhibit different physical properties. In one bubble, the forces might have one set of strengths. In another, the same underlying laws would produce a different set of strengths, because the bubble settled into a different vacuum. The particles might have different masses. Some forces present in our universe might be absent in another, and forces we do not have might exist there. The bubbles would be genuinely different worlds, not merely different arrangements of the same kind of matter, but worlds where matter itself follows different effective rules. This is where a particular framework in theoretical physics enters the picture, one that attempts to unify all the forces and particles into a single coherent description. This framework proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating entities, and that the different particles we observe correspond to different patterns of vibration, much as different notes on a string correspond to different patterns of oscillation. A central feature of this framework is that it requires more dimensions of space than the three we experience. The extra dimensions are thought to be curled up so small that we cannot perceive them, hidden at scales far below anything we can probe. The way these extra dimensions are folded and shaped determines the effective physics in the large dimensions we do experience. Different foldings produce different physical properties, different particle masses, different force strengths, different vacuum states. Here, the framework delivers a remarkable and somewhat unsettling result. There is not just one way to fold the extra dimensions. There are many ways, and when physicists attempt to count the possibilities, the number turns out to be enormous. Each distinct folding corresponds to a distinct vacuum state, a distinct possible universe with its own physical properties. The collection of all these possibilities is sometimes called the landscape, a vast space of possible universes, each occupying a different configuration of the folded dimensions. The number of distinct configurations in this landscape is so large that it dwarfs ordinary notions of large numbers, a figure with hundreds of digits in its exponent. Each point in this landscape represents a universe that could exist, with its own settings of the physical dials, its own version of the effective laws. Now, combine this landscape with eternal inflation, and the two ideas reinforce each other in a powerful way. Eternal inflation continually produces new bubbles, an endless succession of them, each settling into some vacuum state when inflation ends within it. The landscape provides an enormous menu of possible vacuum states for each bubble to settle into. Put together, the picture is one of an eternally inflating expanse, perpetually spawning bubbles, with each bubble settling into one of the vast number of possible configurations from the landscape. Over the unending course of eternal inflation, bubbles of every possible kind would form, exploring the full range of the landscape, realizing every possible set of physical properties somewhere in the endless multitude. Our universe would be one bubble that happened to settle into the particular configuration we observe. One point in a landscape of staggering size, one set of physical dials among an almost unlimited range of alternatives. This proposal carries an explanatory power that deserves attention because it addresses a puzzle that has long troubled physicists. The puzzle concerns the apparent fine-tuning of our universe. When physicists examine the particular values of the physical constants in our universe, they find that many of them seem remarkably well suited to the existence of complex structures, including stars, planets, chemistry, and ultimately life. If the strength of certain forces were slightly different, stars would not form, or atoms would not be stable, or the chemistry necessary for complex molecules would not be possible. The values appear to fall within narrow ranges that permit a rich and structured universe, and outside those ranges, the universe would be barren. This apparent fine-tuning has long demanded an explanation. Why do the constants take values that allow complexity to arise? The landscape, combined with eternal inflation, offers an answer that does not require any special tuning. If there are countless bubbles, each with different physical properties drawn from the vast landscape, then bubbles with every conceivable combination of constants would exist. The overwhelming majority might be barren, with constants unsuited to complexity, producing universes with no stars, no atoms, no chemistry. But somewhere in the multitude, by sheer variety, there would be bubbles where the constants happen to fall within the narrow ranges that permit complex structure. And it is precisely in such bubbles that observers could exist to ask the question. We find ourselves in a universe suited to complexity, not because the universe was tuned for us, but because we could only have arisen in a bubble where the conditions allowed it. The apparent fine-tuning is a selection effect. Among the vast range of bubbles, observers necessarily find themselves in the rare ones compatible with their existence, just as a fish, if it could reflect on its situation, would necessarily find itself in water rather than on dry land, not because the world was made for fish, but because fish can only exist where there is water. This line of reasoning is elegant and has attracted serious attention, but it is also controversial, and the controversy illuminates important questions about the nature of scientific explanation. The objection is that this kind of reasoning, invoking a vast multitude of unobservable universes to explain the properties of our own, risks abandoning the standards that have made science successful. If we cannot observe the other bubbles, if we cannot detect them or test for their existence, Then are we doing science when we invoke them, or are we constructing an untestable story? The landscape and the multitude of bubbles lie forever beyond our horizon, in causally disconnected regions we can never reach. We cannot survey the landscape directly. We cannot count the bubbles. We infer their existence from theories that are themselves not fully confirmed, and we use them to explain features of our universe that might have other explanations we have not yet discovered. Critics argue that this is a step too far, that an explanation invoking the unobservable is not a scientific explanation at all, but a philosophical one dressed in scientific language. Defenders respond that the situation is more subtle. The theories that lead to the landscape and to eternal inflation are not arbitrary. They are attempts to solve real problems in physics, problems concerning the unification of forces and the nature of the earliest moments of the universe. If those theories are correct, and if they predict a multitude of bubbles with varying properties, then the multitude follows whether or not we can observe it directly. The multitude is a prediction of the theories, not an independent assumption. And the theories themselves might be tested in other ways, through their predictions about the physics we can observe, even if their prediction of unobservable bubbles cannot be checked directly. The debate turns on a deep question about what counts as scientific evidence. Is a prediction scientific only if it can be directly observed, or is it enough that it follows rigorously from theories that are themselves testable in other respects? Reasonable scientists disagree, and the disagreement remains unresolved. There's a further difficulty that complicates the landscape picture, one that physicists themselves acknowledge. To use the multitude of bubbles to explain the values of our constants, we would like to say that our constants are typical or probable among the bubbles capable of hosting observers. But assigning probabilities across an infinite collection of bubbles turns out to be mathematically treacherous. When you have infinitely many bubbles of each type, the ordinary methods of counting and comparing break down. There is no straightforward way to say that one kind of bubble is more common than another when both occur infinitely often. This is sometimes called the measure problem, and it represents a genuine obstacle to turning the landscape picture into a predictive theory. Without a reliable way to assign probabilities, the claim that our universe is typical among observer-hosting bubbles loses its precise meaning, and the explanatory power of the landscape becomes harder to pin down. Physicists are actively working on this problem, but it has not been solved, and until it is, the landscape remains a provocative idea rather than a settled explanation. What we have arrived at, then, is a vision of reality vastly larger and more varied than the single uniform universe of traditional cosmology. We have an eternally inflating expanse, spawning an endless succession of bubble universes, each settling into one of an enormous number of possible configurations, each potentially governed by different effective laws, different constants, different physics. Within this picture, our universe is one bubble of a particular kind, and the properties we observe are not fundamental truths about all of reality, but local features of our particular bubble, accidents of which vacuum state our region happened to settle into. It is a humbling picture, one that displaces our universe from any special status and embeds it in a multitude of staggering scope. And yet all of this, the infinite space, the eternal inflation, the landscape of bubbles, arises from considerations about cosmology and the structure of space and the unification of forces. There is another road to a multitude of worlds entirely, one that comes not from the largest scales of the cosmos, but from the smallest, from the behavior of individual particles and the strange logic of quantum mechanics. This road does not require infinite space or eternal inflation. It emerges from a puzzle at the very heart of how we understand matter at its most fundamental level, a puzzle about what happens when we are not looking. Could the act of measurement itself be splitting reality into branches, each as real as the one we experience? Quantum mechanics is the most precisely tested theory in the history of science, confirmed by experiment after experiment to extraordinary accuracy. And yet at its core lies a puzzle that has never been fully resolved. The puzzle concerns what actually happens when we observe the world at its smallest scales. To appreciate why this puzzle might lead to a multitude of parallel realities, We have to understand the strange way that particles behave when no one is watching, and the even stranger way they seem to behave the moment we look. At the heart of quantum mechanics is the idea that the state of a particle is not, in general, a definite thing. A particle does not simply have a position the way a marble sits at a definite spot on a table. Instead, before it is observed, the particle exists in what is called a superposition, a combination of multiple possibilities at once. It is as if the particle occupies many positions simultaneously or moves with many velocities at once, with each possibility carrying a certain weight. This is not a statement about our ignorance, not a matter of the particle having a definite position that we simply do not know. The mathematics of quantum mechanics insists that the particle genuinely exists in this blended state of multiple possibilities, and experiments confirm that this blending has real physical consequences. The different possibilities can interfere with one another, combining and canceling in ways that would be impossible if the particle had a single definite state all along. The classic demonstration of this involves sending particles, one at a time, toward a barrier with two narrow openings. Common sense says each particle must pass through one opening or the other. But when the experiment is performed, the pattern that builds up on the far side reveals that each particle somehow passed through both openings at once, interfering with itself, behaving as a spread-out wave of possibilities rather than a localized object taking a single path. The particle, while unobserved, explores both routes simultaneously. This is among the most thoroughly verified phenomena in physics, reproduced countless times, and it establishes beyond doubt that particles exist in superpositions of multiple possibilities when they are not being observed. Now comes the puzzle. When we actually measure the particle, when we place a detector at one of the openings to see which way it goes, we never find it in a blended state. We always find it at a single definite location, passing through one opening or the other, never both. The act of measurement seems to force the particle to choose, to collapse from its spread-out superposition into a single definite outcome. Before measurement, many possibilities coexist. After measurement, only one remains, and the choice of which possibility becomes real appears to be random, governed only by probabilities. The mathematics tells us the likelihood of each outcome, but not which outcome will actually occur on any given measurement. The particle, blended across possibilities a moment before, suddenly settles into one, and the others vanish. This transition from many possibilities to one definite outcome is the central mystery. The standard equations of quantum mechanics describe beautifully how the superposition evolves over time, how the blend of possibilities shifts and changes. But those equations do not describe the collapse, the sudden reduction from many possibilities to one. The collapse is something added on top of the equations, a separate rule invoked to explain why we always observe definite outcomes despite the underlying blend. This added rule works in the sense that it correctly predicts the statistics of what we observe, but it sits uneasily within the theory. It introduces a special role for measurement, as if observation itself were a fundamental physical process distinct from everything else, capable of collapsing possibilities in a way that ordinary physical interactions do not. This special status of measurement has troubled physicists since the early days of quantum mechanics. What counts as a measurement? Why should the act of observing be physically different from any other interaction between particles? The theory does not say, and the vagueness has long been a source of discomfort. It was in response to this discomfort that a radically different interpretation emerged, one that removes the collapse entirely and accepts a startling consequence in its place. The proposal is disarmingly simple. What if there is no collapse? What if the equations of quantum mechanics, which describe the smooth evolution of superpositions, are the complete and exact description of reality, with nothing added on top? What if the superposition never collapses at all? At first, this seems to contradict experience, because we always observe definite outcomes, not blended ones. But the interpretation has an answer, and the answer is where the multitude of worlds enters. According to this interpretation, when a particle in a superposition interacts with a measuring device, the device does not collapse the superposition. Instead, the device itself becomes part of the superposition. The blend spreads from the particle to the device, so that the device now exists in a superposition of having measured each possible outcome. And when the experimenter reads the device, the experimenter too becomes part of the superposition, existing in a blend of having seen each outcome. The superposition does not collapse, it spreads, encompassing the particle, the device, the experimenter, and eventually everything that interacts with them. Reality as a whole exists in an ever-growing superposition of all possible outcomes. But if this is true, why do we experience only one definite outcome? The interpretation's answer is that each possibility becomes a separate branch of reality, and each version of the experimenter in each branch experiences only the outcome in that branch. There is a branch where the particle went through the left opening, and in that branch, a version of the experimenter who saw the left result. There is another branch where the particle went through the right opening, and in that branch, another version of the experimenter who saw the right result. Both branches are equally real. Both versions of the experimenter are equally real. Each one experiences a single definite outcome and is unaware of the other branch. The superposition has not collapsed. It has split reality into branches, one for each possible outcome, and each branch contains a version of everything, including a version of the observer. This is the interpretation often called the many worlds view, and its central claim is that every quantum event with multiple possible outcomes causes reality to branch, with each outcome realized in a separate branch. Since quantum events are happening constantly, everywhere, at every instant, the branching is relentless and ongoing. Reality is perpetually splitting into an unimaginable number of branches, each one a complete world with its own version of events, its own copies of everything and everyone. You, reading these words, are constantly branching into countless versions, each experiencing a slightly different sequence of quantum outcomes, each equally real, each unaware of the others. The single reality we seem to inhabit is, in this view, just one branch among an ever-multiplying multitude. The appeal of this interpretation lies in its economy of assumptions. It takes the equations of quantum mechanics at face value without adding the awkward collapse rule. It removes the special status of measurement, treating observation as just another physical interaction, no different in kind from any other. There is no mysterious moment of collapse, no question of what counts as a measurement, no random selection of outcomes. Everything that can happen does happen, each in its own branch, and the smooth equations of quantum mechanics describe it all. For those troubled by the collapse rule, this interpretation offers a clean resolution. The price, of course, is the acceptance of an enormous and ever-growing multitude of branching worlds, all equally real, most forever inaccessible to us. It is worth being careful about what this interpretation does and does not claim. It does not claim that the branches are located somewhere else, in space, in distant regions we might travel to. The branches are not far away. They are, in a sense, layered over the same space, evolving independently, unable to interact once they have separated. The reason we cannot perceive the other branches is that once a branching has occurred and the possibilities have become sufficiently distinct, they no longer interfere with one another in any detectable way. The process by which this happens, by which the different branches lose the ability to influence each other, is understood and has a name. It is called decoherence, and it explains why we experience a single definite branch rather than a blend. When a superposition involves only a few particles, the possibilities can still interfere, as in the experiment with the two openings. But when the superposition spreads to involve a large object like a measuring device, with its countless particles interacting with the environment, the possibilities become so thoroughly entangled with the surroundings that they can no longer recombine. The branches separate cleanly and evolve independently, each one a self-contained world. Decoherence is not itself a matter of interpretation. It is a well-understood physical process confirmed by experiment, describing how quantum superpositions of large systems effectively lose their ability to interfere. What the many worlds interpretation adds is the claim that the branches that decoherence separates are all equally real. that none of them is selected as the one true outcome while the others vanish. The branches simply continue, all of them, forever separating into finer and finer distinctions. Decoherence explains why each branch appears self-contained and classical. The interpretation supplies the further assertion that every branch genuinely exists. How does this road to a multitude of worlds compare to the others we have explored? It is strikingly different in character. The infinite universe and the eternal inflation pictures place their copies in alternate worlds far away in space, in regions beyond our horizon, separated by unimaginable distances. The many worlds picture places its branches not in distant space, but in a kind of parallel coexistence, layered over the same space, separated not by distance, but by the branching structure of quantum events. And yet the conclusion has a similar flavor. In all these pictures, the reality we experience is only a small part of a much larger whole, and there exist countless versions of us in other regions or other branches, living out the variations of our lives. The convergence is remarkable. Cosmology, through the size of space and the dynamics of inflation, points toward a multitude. Quantum mechanics, through the interpretation of measurement, points toward a multitude as well. Different foundations, different mechanisms, yet a similar destination. The many worlds interpretation is not universally accepted. It remains one of several competing interpretations of quantum mechanics, and physicists continue to debate which interpretation, if any, correctly describes reality. Some find the proliferation of branches extravagant, an unacceptable multiplication of unobservable worlds to solve a problem that other interpretations address differently. Others find it the most honest reading of the equations, the only interpretation that takes the mathematics seriously without adding arbitrary rules. The debate is ongoing and may never be settled by experiment, because the competing interpretations are designed to make the same predictions about what we observe, differing only in their account of what lies behind those observations. This is a crucial point. The various interpretations of quantum mechanics agree on all the predictions that can be tested. They disagree only about the underlying reality, about whether the collapse is real, about whether the branches exist. And if they make the same testable predictions, then experiment alone may not be able to decide between them. This raises a question that haunts all of these ideas about multiple worlds, whether they arise from cosmology or from quantum mechanics. If the other worlds, the other branches, the other bubbles are by their nature beyond our ability to observe or test, then how can we ever know whether they are real? Is there any possible evidence that could confirm or refute their existence, or are we forever confined to speculation, however well-reasoned? The question of testability sits at the boundary between science and something beyond it, and confronting it honestly is essential if we are to understand what these ideas truly offer and where their limits lie. Can a claim about the unobservable ever be brought within the reach of evidence? The question of whether claims about other universes can ever be tested goes to the heart of what science is and what separates it from other ways of thinking about reality. Science has earned its authority through a particular discipline, the insistence that claims be checked against observation, that predictions be made and verified, that ideas be exposed to the possibility of being proven wrong. A claim that cannot be tested, that no possible observation could confirm or refute, has traditionally been regarded as lying outside the proper domain of science, however interesting it might be as philosophy or speculation. The ideas we have examined, the infinite repetitions, the bubble universes, the quantum branches, all seem to place their other worlds beyond the reach of observation. This apparent untestability is the most serious objection raised against them, and it deserves to be confronted directly rather than waved away. The objection takes a sharp form. If the copies of you in distant regions of an infinite universe lie so far away that their light can never reach us, then no observation we could ever make would reveal them. If the other bubble universes are causally disconnected, separated by an eternally inflating expanse that nothing can cross, then we can never detect them, never receive a signal from them, never confirm they exist. If the quantum branches separate cleanly through decoherence and can no longer interfere with our branch, then we can never observe them either. In each case, the other worlds seem to be defined precisely by their inaccessibility. They are the parts of reality we cannot reach. And if we cannot reach them, the objection goes, then asserting their existence is not a scientific claim, but an article of faith dressed in scientific language. We might as well assert anything we like about regions we can never observe. This objection carries real force, and honest defenders of these ideas do not dismiss it. But the response to it is more subtle than the objection assumes, and understanding that response clarifies what kind of claims these ideas actually make. The key insight is that the other worlds are not themselves the primary claim. They are consequences of theories, and the theories make other predictions that can be tested. The logic runs like this. We do not directly assert that copies or bubbles or branches exist. Instead, we develop theories to explain things we can observe, and those theories, if correct, happen to imply the existence of other worlds as a byproduct. The other worlds come along with the theory whether we like it or not, and the theory can be tested through its other predictions, even if the prediction of other worlds cannot be tested directly. Consider how this works in each case. The idea of an infinite universe filled with copies rests on two premises, the flatness of space and the graininess of matter. Both premises are testable, and both have been tested. We can measure the geometry of space by studying the patterns in the ancient light, and those measurements tell us the universe is flat to high precision, which is consistent with infinity. We can confirm the graininess of matter through countless experiments in quantum physics. The premises are not articles of faith, they are conclusions drawn from observation. The existence of copies follows from these observed premises by logical necessity, given the additional assumption that space is truly infinite rather than merely very large. So while we cannot observe the copies themselves, we can test the premises from which their existence follows. And if the premises hold and space is infinite, the copies must exist whether we can see them or not. The claim about copies is not independent of evidence. It is tethered to evidence through the premises that imply it. A similar logic applies to inflation. The theory of inflation was proposed to solve the puzzles of uniformity and flatness, and it makes specific, testable predictions about the patterns in the ancient light, the statistical character of the tiny temperature variations across the sky. Those predictions have been checked against observation and found to match. Inflation is not an untestable fantasy. It is a theory with confirmed predictions about things we can measure. And eternal inflation, the version in which inflation never fully ends and spawns endless bubbles, follows from the same mechanism that the confirmed theory describes, combined with the probabilistic nature of the inflationary field's decay. If the theory of inflation is correct and the evidence supports it, then the eternal version and its bubbles may follow as a consequence, even though we cannot observe the other bubbles directly. Again, the other worlds are tethered to evidence through the theory that implies them, not asserted independently. The quantum branches present the most interesting case because here the situation is genuinely different from a matter of distant inaccessibility. The many worlds interpretation makes exactly the same testable predictions as every other interpretation of quantum mechanics. This is not a weakness peculiar to many worlds. It is a feature shared by all the interpretations. They all agree on what we will observe in any experiment because they are all built on the same underlying equations, the equations that have been confirmed to extraordinary precision. The interpretations differ only in their account of what underlies the observations, whether the collapse is real, whether the branches exist. Since they agree on all testable predictions, no experiment can distinguish them. This means the choice between interpretations cannot be made on the basis of evidence in the ordinary sense. It must be made, if it can be made at all, on other grounds, such as which interpretation is simpler, which makes fewer arbitrary assumptions, which gives the most coherent account of the equations we know to be correct. This situation is unusual in science and worth dwelling on. We have a theory, quantum mechanics, whose predictions are confirmed beyond any reasonable doubt. But the theory admits multiple interpretations, multiple accounts of what reality is actually like beneath the predictions, and these interpretations cannot be distinguished by experiment. Some scientists regard this as a sign that the question of interpretation is not a scientific question at all, but a metaphysical one, a matter of preference rather than fact. Others argue that simplicity and coherence are legitimate scientific virtues, that an interpretation which takes the equations at face value without adding arbitrary rules is to be preferred, and that on these grounds, the many worlds interpretation has genuine merit despite the impossibility of direct confirmation. The debate continues, and it illustrates how science, pushed to its frontiers, encounters questions that its usual methods cannot fully resolve. There is, however, a tantalizing possibility that some of these ideas might yield to observation, after all, that the other worlds might leave a faint trace we could detect. This possibility is most concrete in the case of bubble universes. Recall that in the eternal inflation picture, bubbles form within the inflating expanse, each one a separate universe. If two bubbles formed close enough together, they might expand toward each other and collide. Our bubble, in its early history, might have collided with a neighboring bubble. Such a collision, if it occurred, would not have destroyed our universe, but it might have left an imprint, a disturbance in the early universe that could show up as a particular kind of pattern in the ancient light. Cosmologists have worked out what such an imprint might look like, a circular feature of a specific character imprinted on the sky, a signature of a past collision with another universe, and they have searched for it, examining the maps of the ancient light for any sign of such a feature. This is a remarkable development. It means that the existence of other universes, far from being entirely untestable, might in principle leave observable traces. A collision between bubbles would be evidence, however indirect, that other bubbles exist, that the eternal inflation picture is correct, that our universe is one among many. So far, the searches have not found a convincing signature. The maps of the ancient light show no clear sign of a bubble collision, but the absence of a detected collision does not mean other bubbles do not exist. It might simply mean that no bubble happened to collide with ours, or that any collision left too faint a trace to detect, or that collisions are rare. The search continues, and its very existence demonstrates that these ideas are not entirely beyond the reach of evidence. There is at least one scenario in which the multitude of universes could announce itself, faintly, in the patterns of the sky. The case of the infinite universe and its copies is harder. The copies lie so far away that no signal from them could ever reach us, and there is no analog of a bubble collision that might bring evidence of them within reach. The existence of copies, if it follows from an infinite flat universe, would have to be accepted on the strength of the premises rather than through any direct or indirect observation of the copies themselves. This is a genuine limitation. It means that the claim about copies, while logically following from testable premises, occupies a peculiar position. The premises are scientific, confirmed by observation, but the specific conclusion about distant copies can never be checked. Whether one regards this as acceptable depends on one's philosophy of science, on how willing one is to accept conclusions that follow rigorously from confirmed premises, even when the conclusions themselves lie beyond observation. What emerges from all this is a nuanced picture, neither the dismissive claim that these ideas are mere fantasy, nor the overconfident claim that other universes are established fact. The ideas occupy a spectrum. Some, like inflation, rest on confirmed predictions and enjoy strong evidential support, though their more speculative extensions reach beyond what is confirmed. Some, like the bubble collisions, offer at least the prospect of observable evidence, however faint and so far undetected. Some, like the distant copies in an infinite universe, follow from confirmed premises but cannot themselves be observed. And some, like the quantum branches, are tied to a theory whose predictions are thoroughly confirmed, but whose interpretation cannot be settled by experiment. To lump all these together as untestable speculation is to miss the important distinctions among them. Each stands in a different relationship to evidence, and each must be judged on its own terms. The honest conclusion is that science, at this frontier, is doing something it has rarely had to do. It is following the logic of its best theories to conclusions that strain the traditional requirement of testability. The theories themselves are products of the ordinary scientific process, proposed to solve real problems, tested where testing is possible, refined against observation. But they carry implications that reach beyond the observable, and science must decide how to regard those implications. This is not a failure of science, but a sign of its maturity, its willingness to follow its reasoning even into territory where the usual methods reach their limits, while remaining honest about which claims are confirmed and which are not. The boundary between the testable and the untestable is not always sharp, and these ideas live precisely in the contested region near that boundary. But suppose, for a moment, that the copies are real. Suppose that somewhere, an identical version of you exists, and not just one, but infinitely many, each living out a variation of your life. This possibility raises questions that go beyond physics, questions about identity and selfhood that physics alone cannot answer. If there are countless versions of you, which one is the real you? What does it even mean to be a unique individual in a universe that contains endless copies? These questions take us from the structure of the cosmos to the nature of the self, and they prove surprisingly difficult to answer. If the universe truly contains countless copies of you, the comfortable notion of being a singular, unique individual begins to dissolve, and in its place arise questions that physics raises but cannot resolve on its own. These are questions about identity, about what it means to be a particular person, about the relationship between you and the copies that share your every atom and memory. They are not idle puzzles. They cut to the core of how we understand ourselves, and they reveal that the existence of copies, if real, would unsettle not just our picture of the cosmos, but our picture of the self. Begin with the most basic question. If there is a copy of you somewhere, identical in every physical detail, holding the same memories, thinking the same thoughts, is that copy you, or is it someone else? The instinctive answer is that it is someone else, a separate person who merely happens to resemble you exactly. After all, that copy is over there in some distant region while you are here. You cannot feel what the copy feels. You have no access to the copy's experiences. When the copy stubs its toe, you feel nothing. The two of you are separate centers of experience, separate streams of consciousness, occupying different locations and living different lives, however similar. By this reasoning, the copy is not you, but a duplicate, a separate individual who is qualitatively identical but numerically distinct, the same in every property, yet a different entity. But this answer, satisfying as it seems, runs into difficulties when examined closely. Consider what makes you the same person from one moment to the next. The you of this morning and the you of this evening are not physically identical. Atoms have been exchanged, cells have changed, your brain has been altered by the day's experiences. Yet we regard them as the same person, connected by continuity of memory and bodily persistence. Now ask what makes the you of today the same person as the you of yesterday, given that the physical material has partly changed. The usual answer appeals to continuity, the unbroken chain of cause and effect linking one moment to the next, the persistence of memory and personality through gradual change. Identity, in this view, is not about being physically identical at all times, but about being connected through a continuous history. This is where the copies complicate matters. The copy in the distant region shares your memories and personality, but it is not connected to you through a continuous physical history. It arose independently in its own region through its own chain of events that happen to produce the same arrangement. So by the continuity criterion, the copy is not you because there is no continuous chain linking you to it. But notice the strange consequence. The copy has exactly the same relationship to your past self as you do. The copy remembers your childhood, or rather, remembers a childhood identical to yours with the same experiences, the same formative moments. From the copy's perspective, those memories are its own, just as real and vivid as yours are to you. If memory and psychological continuity are what ground identity, then the copy has just as strong a claim to being the continuation of your past self as you do. Both of you remember the same past. Both of you feel like the natural continuation of that past, yet you are clearly separate beings now. The criterion that was supposed to secure your identity over time seems to apply equally to a being you would not call yourself. This puzzle becomes sharper in the quantum branching picture, where the situation is even more intimate. In the many worlds, interpretation, the branches do not arise in distant regions through independent chance. They arise from you, here and now, through the branching of quantum events. When a quantum event with multiple outcomes occurs, you split into versions, one for each outcome, and each version is a direct continuation of the single you that existed before the branching. This is different from the distant copy that arose independently. The branched versions are genuinely continuous with your past self, each one connected to you through an unbroken history right up to the moment of branching. Before the branching, there was one you. After the branching, there are several, each with an equal claim to being the continuation of the one that came before. Here, the continuity criterion does not single out one true continuation. It endorses all of them equally. Each branched version remembers being the single pre-branching you, and each is connected to that self through a continuous history. There is no fact that makes one branch the real you and the others mere copies. They are all equally you, and yet they are now separate, destined to live different lives in different branches. This has a disorienting implication for how we think about the future. Ordinarily, you anticipate your future as a single thread, expecting to experience whatever comes next. But in the branching picture, there is no single future you. There are many, each experiencing a different outcome, each equally entitled to be considered your future self. When you wonder what you will experience after some quantum event, the question may have no single answer. You will experience all the outcomes, in the sense that there will be versions of you experiencing each one, but no single version experiences more than one. The expectation of a single definite future, so basic to how we live, may be an illusion produced by the fact that within any one branch, you only ever encounter that branch's outcome and remain unaware of the others. The you in each branch feels like the unique continuation, never suspecting that other equally valid continuations are unfolding in parallel. These considerations connect to a deep and long-standing debate about the nature of personal identity, a debate that predates the cosmological ideas but is thrown into sharp relief by them. Philosophers have long asked what personal identity consists in, what makes a person the same person over time, and various answers have been proposed. Some locate identity in physical continuity, the persistence of the same body or brain. Some locate it in psychological continuity, the persistence of memory, personality, and intention. Some have concluded, after wrestling with puzzles like these, that personal identity is not the deep all-or-nothing fact we instinctively take it to be. On this view, the question of whether the distant copy or the branched version is really, you may have no factual answer because identity is not a sharp, determinate matter in the first place. What matters on this view is not some metaphysical fact about which being is really you, but the pattern of psychological connections, the relationships of memory and continuity, which can hold to varying degrees and can be shared among multiple beings. If identity is like this, then asking which copy is really you may be a confused question, like asking which of several identical copies of a book is the real book. The question assumes a sharpness that may not exist. There is something both unsettling and liberating in this conclusion. Unsettling because it threatens the deeply held sense that you are a single, unique, continuous self, the one and only you, persisting through time as a definite individual. Liberating perhaps because it suggests that the boundaries of the self may be less rigid than we assume, that what matters about us is the pattern we embody rather than the particular matter that happens to embody it, and that this pattern might be realized many times over without any one realization being more truly us than another. Whether one finds this comforting or disturbing likely depends on temperament, but either way it represents a genuine challenge to ordinary self-understanding, prompted directly by the physics of multiple worlds. The copies also raise questions about the significance of our choices and the value of our individual lives. If every possible version of your life is being lived out somewhere, by some copy or in some branch, does your particular life retain its meaning? Some find this prospect deflating. If there is a version of you who made every choice you agonized over, who took every path you did not take, then your own choices might seem to lose their weight, since all the alternatives are being realized regardless. Why struggle to make the right decision if a copy of you is making every other decision anyway? But this reasoning, on reflection, may be misguided. The copies and branches do not diminish the reality of your own experience. You are the one living your life, making your choices, experiencing their consequences. The existence of other beings living other lives does not reach into your life and drain it of meaning. Each version experiences its own life as fully real, as the only life it is living, and that experiential reality is not lessened by the existence of others. The meaning of a choice lies in its being made and lived, not in its being the only choice made anywhere in all of reality. There is also a subtle point about probability and expectation that the copies bring to the surface. In ordinary life, we reason about what is likely to happen, assigning probabilities to outcomes and acting accordingly. But if all outcomes happen in some branch or some region, what does probability mean? This question is most pressing in the quantum branching picture, where every outcome of every quantum event is realized in some branch. If every outcome happens, in what sense is one outcome more probable than another? The mathematics of quantum mechanics assigns different weights to different outcomes, and these weights behave like probabilities, correctly predicting the statistics we observe. But if all outcomes occur, the meaning of these weights becomes puzzling. Why should an outcome with a higher weight be more likely to be experienced if all outcomes are experienced by some version of you? This is a genuine difficulty for the branching picture, and physicists and philosophers have proposed various ways to make sense of it, attempting to recover the ordinary meaning of probability within a framework where everything happens. The problem has not been fully resolved, and it represents one of the deepest challenges to the branching interpretation, a challenge that touches on the relationship between the mathematics and our lived experience of a probabilistic world. What all these reflections reveal is that the existence of copies, whether in distant space or in quantum branches, does not merely add more objects to the universe. It reaches into our most basic concepts, the self, identity, the future, probability, meaning, and unsettles them. Physics, in pursuing the structure of reality, has stumbled into territory that belongs as much to philosophy as to science, raising questions that its equations cannot answer. The equations can tell us that copies might exist, can describe the branching, can assign the weights, but they cannot tell us which copy is really us, or what we should expect to experience, or whether our lives retain their meaning. Those questions require a different kind of reflection, and they may not have clean answers at all. And yet, for all the strangeness of these ideas, we have so far treated the existence of other worlds as something that, while perhaps beyond direct observation, might still leave faint traces or follow from testable premises. We touched briefly on the possibility that bubble universes might collide and leave an imprint. It is worth returning to that possibility in greater depth, because it represents the most concrete hope of finding actual evidence for other universes, of moving these ideas from speculation toward observation. What would it actually take to detect another universe, and what have we found when we have looked? The prospect of detecting another universe sounds like a contradiction in terms. The other worlds, by their nature, lie beyond our horizon in regions we cannot reach, separated from us by distances or by branching structures that seem to forbid any contact. And yet there is one scenario in which the wall between universes might develop a crack, one situation in which another universe might announce its existence by leaving a mark on our own. That scenario is the collision of bubble universes, and it represents the most serious attempt physicists have made to bring the multitude of worlds within the reach of observation. Examining it closely shows both how far the search has come and how difficult the task remains. Recall the picture that eternal inflation paints. The inflating expanse is perpetually spawning bubbles, each one a universe that forms when inflation ends in that patch. These bubbles form at different times in different places within the inflating ocean, and once formed, they expand. Now consider two bubbles that form near each other. Each begins as a tiny region where inflation has ended, and each expands outward into the surrounding inflating space. If they formed close enough together, their expanding edges might meet. The bubbles would collide. This is not a fanciful addition to the theory. It is a natural consequence of the bubbles forming within a shared inflating expanse. If bubbles form, and if they form in proximity sometimes, then collisions should occur. Our own bubble, in its early history, might have collided with one or more neighboring bubbles before settling into the relatively quiet expansion we observe today. What would such a collision do? It would not necessarily destroy our universe, but it would disturb it. The collision would inject energy and momentum into the early universe along the region where the bubbles met, creating a disturbance that would propagate and leave traces. The crucial question is whether any of those traces would survive to the present day in a form we could detect. The answer, according to detailed calculations, is that a collision might leave an imprint on the ancient light, the radiation that fills space and carries information from the early universe. Specifically, a collision would tend to produce a disturbance in a particular region of the sky, a region shaped like a disk within which the temperature of the ancient light would deviate from the surrounding pattern in a characteristic way. The collision would leave a circular bruise on the sky, a region of altered temperature with a distinctive profile, marking the place where another universe once touched our own. This is a genuine, concrete prediction. It tells us what to look for, a circular feature of a specific character imprinted on the map of the ancient light. And because we have detailed maps of that ancient light, produced by careful observation of the entire sky, we can actually search for such features. This is what makes the bubble collision scenario so significant. It transforms the question of other universes from pure speculation into something approaching an observational program. We know what the signature of a collision would look like, and we can examine the data to see whether any such signature is present. The other universe, if it collided with ours, would have left a calling card, and we can search for that card in the patterns of the sky. The search is not simple. The ancient light has many features, many variations in temperature across the sky, most of them arising from ordinary processes in the early universe, the quantum fluctuations stretched by inflation that seeded the formation of galaxies. Against this background of natural variation, a collision signature would have to stand out, a feature distinct from the ordinary fluctuations, recognizable by its particular shape and profile. The challenge is to distinguish a genuine collision signature from the random patterns that occur naturally. With so much natural variation across the entire sky, some features will by chance resemble a collision signature, just as random patterns sometimes resemble recognizable shapes. The task is to determine whether any feature in the data is a real collision signature or merely a chance resemblance among the natural fluctuations. This requires careful statistical analysis, comparing the observed features against what would be expected from natural variation alone, and assessing whether any candidate feature is significant enough to be taken seriously. Physicists have carried out this search, examining the maps of the ancient light for features matching the predicted collision signature. They have developed methods to scan the entire sky systematically, looking for circular regions with the characteristic temperature profile a collision would produce. The results so far have been inconclusive in a particular way. No feature has been found that clearly stands out as a collision signature beyond what could occur by chance. There have been candidate features, regions that bear some resemblance to what a collision might produce, but none has reached the level of significance needed to claim a detection. When the candidates are subjected to rigorous statistical scrutiny, they turn out to be consistent with the natural fluctuations, not requiring a collision to explain them. The search has not found convincing evidence of a bubble collision. It is important to interpret this result correctly, because it is easy to misread. The absence of a detected collision does not mean that other bubbles do not exist, and it does not refute the eternal inflation picture. There are several reasons why a real multitude of bubbles might leave no detectable collision signature in our data. The most basic is that our bubble might simply not have collided with any other, or might have collided only with bubbles too distant to leave a visible mark within our observable region. Collisions depend on bubbles forming nearby, and there's no guarantee that any formed close enough to ours to produce a detectable imprint. Even in a picture with countless bubbles, our particular bubble might have been relatively isolated in its early history, its nearest neighbors too far away to reach us. The absence of a collision signature would then be entirely expected, telling us nothing about whether other bubbles exist, only that none happen to collide with ours in a detectable way. There is also the possibility that collisions occurred but left signatures too faint to detect with current instruments, or signatures that have been obscured by the natural fluctuations in the limits of our measurements. A weak collision, or one that occurred under certain conditions, might produce only a subtle disturbance, lost in the noise of natural variation. As our maps of the ancient light improve, with more sensitive instruments and more detailed observations, fainter signatures might become detectable that current data cannot reveal. The search is not over. It is ongoing, and future observations might yet uncover a signature that present data is too coarse to find. The current absence of detection is a snapshot of an ongoing effort, not a final verdict. What the search demonstrates, regardless of its outcome so far, is that the question of other universes is not entirely beyond the reach of evidence, that there exists at least one concrete scenario in which the multitude of worlds might reveal itself observationally. This is a significant point in the debate over whether these ideas are scientific. Critics charge that other universes are untestable in principle, that asserting their existence steps outside science. The bubble collision search is a direct response to this charge. It shows that at least one version of the multiverse idea, the bubble universes of eternal inflation, makes a prediction that can be tested, a prediction about features in data we can actually examine. The prediction has not been confirmed, but the fact that it can be tested at all distinguishes this idea from pure speculation. A theory that makes a testable prediction is doing science, even if the prediction turns out negative or remains unconfirmed. There are other proposed avenues for finding traces of other universes or the conditions that would produce them, though none is as developed as the bubble collision search. Some have explored whether the overall geometry or large-scale features of our universe might bear subtle signs of its origin in eternal inflation, signs that could distinguish a universe born from eternal inflation from one with a different origin. Others have examined whether the detailed statistics of the ancient light, the precise pattern of its fluctuations, might contain hints of physics beyond the simplest inflationary models, physics that could point toward the landscape of possible universes or the eternal inflation that populates it. These approaches are more indirect and more speculative than the bubble collision search, but they reflect a serious effort to find observable consequences of the multiverse ideas, to tether these grand pictures to data wherever possible. It must be acknowledged, though, that the most dramatic versions of the multitude, the infinite copies of you in a boundless universe, the parallel quantum branches, lie further beyond observational reach than the bubble collisions. The infinite copies are too far away to leave any trace, separated from us by distances no signal could cross. The quantum branches separate cleanly through decoherence and no longer interact with our branch in any detectable way. For these, there is no analog of the bubble collision, no scenario in which they might leave an observable mark. They remain tied to evidence only through the testable premises or theories from which they follow, not through any direct or indirect observation of the other worlds themselves. This is an honest limitation, and it means that these ideas, however well-reasoned, occupy a different position from the bubble collisions, which at least offer the prospect of observational test. Standing back from the details, what we see is a science reaching toward the edge of what observation can confirm, developing ingenious methods to test ideas that once seemed entirely beyond testing, and finding, so far, neither confirmation nor refutation, but a continuing uncertainty. The bubble collision search exemplifies this. It is a serious, rigorous attempt to detect another universe, grounded in a specific prediction, carried out with careful analysis, yielding so far a null result that neither confirms nor rules out the multitude. This is what frontier science looks like: the patient pursuit of evidence for ideas at the limits of the testable, with results that are often inconclusive, but that gradually narrow the possibilities and refine our understanding of what the data can and cannot tell us. But this raises a deeper question that lurks behind all these searches and all these ideas. Perhaps there are simply truths about reality that lie permanently beyond our ability to know, regions of the cosmos and aspects of its structure that no observation could ever reach, no matter how clever our methods or how sensitive our instruments. If the universe is far larger than our horizon, if other bubbles are causally disconnected, if quantum branches separate beyond recall, then there may be facts about reality that are real but forever unknowable to us. What does it mean for science and for our understanding of our place in the cosmos if some truths are permanently hidden? Is there a limit to what we can ever know, and if so, where does it lie? The possibility that some truths about the universe may be permanently beyond our reach is a sobering thought for an enterprise built on the conviction that the world is knowable. Science has progressed by pushing back the boundaries of ignorance, by turning mysteries into understood phenomena, by reaching ever further into the very large and the very small. The implicit faith underlying this progress is that the universe is, in principle, comprehensible, that with enough effort and ingenuity, we can come to understand any aspect of reality. But the ideas we have explored suggest that this faith may meet a hard limit, that there may be features of reality that are not merely unknown but unknowable, hidden from us not by the limits of our current technology, but by the fundamental structure of the cosmos itself. Confronting this possibility honestly is part of understanding what these ideas about multiple worlds truly imply. The most basic source of permanent ignorance is the cosmic horizon we discussed at the very beginning. There's a boundary beyond which no light has had time to reach us, a sphere of visibility surrounding us, and everything outside it is, for now, invisible. As the universe ages, the horizon slowly grows and more distant regions gradually come into view. One might hope that, given enough time, the horizon would expand to encompass everything, that eventually all of reality would become observable. But this hope runs into an obstacle rooted in the behavior of the universe's expansion. The expansion of space is not slowing down, it is accelerating, driven by a mysterious influence that pushes space to expand ever faster. This acceleration has a profound consequence for what we can observe. As space expands faster and faster, distant regions are carried away from us at increasing rates. Regions beyond a certain distance are receding so rapidly that their light can never reach us, no matter how long we wait. The acceleration creates a kind of permanent horizon, a boundary beyond which lies space we can never observe, not because light has not had time to reach us yet, but because the expansion is carrying those regions away faster than their light can travel toward us. This is a remarkable and somewhat melancholy feature of our universe. The accelerating expansion means that, far from eventually seeing everything, we are actually losing sight of the cosmos over time. Distant galaxies that are currently visible will, in the far future, recede beyond the reach of observation, their light stretched and dimmed by the expansion until it can no longer reach us. The observable universe, in this sense, is destined to shrink in content, as more and more of what we can currently see is carried beyond the permanent horizon. Future observers, far enough in the future, will see a cosmos emptier than the one we see, with the distant galaxies having vanished from view. And the regions beyond the permanent horizon, the vast reaches of space that are receding too fast for their light to reach us, are permanently hidden. If there are copies of us out there in the infinite reaches of a boundless universe, they lie far beyond this permanent horizon, in regions we could never observe even in principle. Even with unlimited time and perfect instruments, the accelerating expansion seals them away from us forever. This means that the infinite copies, if they exist, belong to a category of things that are real but permanently unobservable. They are not hidden by any practical limitation that future progress might overcome. They are hidden by the fundamental structure of an expanding universe, sealed beyond a horizon that no observation can pierce. Their existence, if it follows from an infinite flat universe, would be a fact about reality that we can never directly confirm, a truth forever beyond the reach of evidence. This is a genuine epistemic limit, a boundary on what can be known, set not by our ignorance or our technology, but by the cosmos itself. The bubble universes of eternal inflation present a similar situation, perhaps even more severe. The bubbles are causally disconnected, separated by an eternally inflating expanse that expands faster than anything can cross. We cannot travel to another bubble, cannot send or receive signals across the inflating gulf between them. Except, in the special case of a past collision that left a detectable imprint, the other bubbles are entirely beyond our reach, hidden behind the inflating space that separates them. And even the collision scenario only offers a faint hope, applicable only to bubbles that happen to collide with ours, leaving most of the multitude permanently inaccessible. The vast majority of bubbles, if they exist, are truths we can never verify, regions of reality forever sealed away by the dynamics of eternal inflation. The quantum branches add yet another layer of permanent inaccessibility, of a different kind. The branches do not lie beyond a spatial horizon. They are, in a sense, layered over the same space, but they have separated through decoherence, losing the ability to interact with one another. Once a branching has occurred and the branches have decohered, no observation in one branch can reveal the others. The branches evolve independently, each containing its own version of everything, and there is no way to peer from one branch into another. The other branches are real if the many worlds interpretation is correct, but they are permanently hidden, separated from us not by distance, but by the irreversible process of decoherence that severs the branches from one another. We are confined to our branch, able to observe only its contents, forever cut off from the parallel branches in which other versions of events unfold. Taken together, these limits paint a picture of a reality far larger than the part we can know, with vast regions and entire categories of existence permanently sealed beyond our reach. The cosmos beyond our horizon, the other bubbles, the parallel branches, all may be real, and all may be forever unobservable. This is a profound shift from the implicit assumption that the universe is fully knowable. It suggests that there is a fundamental gap between what is real and what is knowable, that reality extends beyond the boundaries of possible knowledge, that there are truths we can never access no matter how far science progresses. The universe, in this view, is not fully transparent to inquiry. It contains hidden depths that no observation can plumb. How should science respond to this? One response is a kind of disciplined humility, an acknowledgement that science can only speak with confidence about what lies within the reach of observation, and that claims about the permanently unobservable, however well-reasoned, occupy a different and more uncertain status. On this view, science should focus its confident assertions on the observable universe, treating claims about other universes and other branches as extrapolations that follow from our theories, but that cannot themselves be confirmed. This response preserves the rigor of science by drawing a clear line between the testable and the untestable, between what we can know and what we can only infer. It does not deny that the other worlds might exist, but it refuses to grant their existence the same epistemic status as observed phenomena. Another response is to argue that the line between observable and unobservable is not as sharp or as significant as it first appears, and that we routinely accept the existence of things we cannot directly observe when they follow from well-confirmed theories. We accept the existence of the interiors of distant stars, which we cannot directly observe because our theories of stellar physics, confirmed in many other ways, imply them. We accept the existence of the deep past, the eras of cosmic history before any possible observer, because our theories imply them and because the traces they left are consistent with our observations. In this spirit, one might argue, we can accept the existence of other universes if they follow from theories confirmed in their observable predictions, even though the other universes themselves cannot be observed. The unobservability of the other worlds, on this view, is not a decisive objection because we already accept many unobservable things on the strength of the theories that imply them. What matters is the quality of the theory and the confirmation of its observable predictions, not whether every consequence of the theory can be independently checked. This debate has no settled resolution, and it reflects a genuine tension at the heart of how we understand the scope and limits of science. Where exactly is the line between legitimate inference to the unobservable and unwarranted speculation? When does following a theory's logic to its conclusions become science fiction rather than science? These questions do not have clean answers, and thoughtful scientists and philosophers disagree about them. The ideas about multiple worlds force these questions to the surface, demanding that we think carefully about what science can claim and what it must leave uncertain about the relationship between the real and the knowable. There is a deeper philosophical point lurking here, one that touches on the nature of reality itself. We tend to assume that reality is a single, definite thing, the same for all observers, fully determinate whether or not anyone observes it. But the ideas we have explored complicate this assumption. If reality includes vast regions and entire branches that are permanently inaccessible to us, then the reality we can know is only a fragment of the whole. And the whole may have a structure very different from what our limited vantage suggests. Our picture of reality, built from what we can observe, may be like the picture a person confined to a single room might form of a vast building, a picture necessarily incomplete and possibly misleading about the structure of the whole. The permanently unobservable regions are not just more of the same, more galaxies and more space. They might include universes with different laws, branches with different histories, structures we cannot even imagine from within our limited vantage. The reality beyond our horizon might be stranger and more various than anything our local observations could suggest. And yet there is something to be said for the power of reason to reach beyond observation, to infer the existence and character of what we cannot see. The whole enterprise of these ideas is an exercise in reasoning beyond the observable, in using our best theories to deduce what must lie beyond the horizon, beyond the inflating gulf, beyond the decohered branches. This reasoning is not arbitrary. It is constrained by logic, by the requirement of consistency with what we do observe, by the structure of theories confirmed in their testable predictions. It represents an attempt to extend understanding beyond the limits of direct observation, to grasp through reason what the senses cannot reach. Whether such reasoning can truly deliver knowledge of the unobservable, or whether it can only deliver well-founded speculation, is precisely the question at issue. But the attempt itself reflects a deep human impulse, the desire to understand the whole of reality, not just the fragment available to direct inspection. We have traveled a long way, from the simple question of how big the universe is, through the geometry of space, the finiteness of possible arrangements, the dynamics of inflation, the landscape of possible universes, the branching of quantum reality, the questions of identity, and the searches for evidence, to the limits of what we can ever know. Throughout, we have tried to distinguish the firmly established from the speculative, the observed from the inferred, the testable from the permanently hidden. What remains is to ask why any of this matters, why we should care whether we are unique or endlessly copied, whether the universe is one or many, whether there are truths we can never know. The answer touches on something fundamental about our place in existence and the meaning we find in confronting questions that may exceed our grasp. Why should it matter whether the universe contains copies of us, whether reality is one or many, whether there are truths we can never reach? The question deserves a serious answer, because at first glance, these ideas might seem to have no bearing on ordinary life. The copies, if they exist, are too far away to ever affect us. The other bubbles are sealed beyond an inflating gulf. The quantum branches have decohered beyond recall. None of these can reach into our lives, change our circumstances, or touch us in any practical way. So why care? The answer is that these ideas, regardless of their practical irrelevance, reshape our understanding of our place in existence, and that understanding has always mattered to human beings in ways that go beyond the practical. How we conceive of the cosmos and our position within it shapes how we understand ourselves, and these ideas offer a conception radically different from any that came before. Consider the long arc of how humanity has understood its place in the cosmos. For most of history, the prevailing picture placed us at the center of everything. The Earth was thought to sit at the center of the universe, with the heavens revolving around it, and humanity occupied a special central position in the scheme of things. This picture was not merely astronomical. It carried a sense of human significance, the conviction that we mattered, that the cosmos was arranged around us and for us. The slow dismantling of this picture is one of the great themes of the history of science. We learned that the Earth is not the center, but one planet orbiting an ordinary star. We learned that our star is not special, but one among hundreds of billions in our galaxy. We learned that our galaxy is not unique, but one among hundreds of billions of galaxies. Each step displaced us further from the center, diminished our cosmic significance, embedded us more deeply in a vast and indifferent universe. This progressive displacement, sometimes called the principle that we occupy no special place, has been a recurring lesson of cosmic discovery, each advance revealing that what we took to be central and unique is in fact ordinary and typical. The ideas about multiple worlds represent perhaps the furthest extension of this displacement. If the universe is infinite and contains copies of us, then we are not even unique as individuals. There are countless others identical to us, living variations of our lives, and our particular existence is not singular, but endlessly repeated. If there are other bubbles with different laws, then even the physical laws we took to be fundamental and universal are merely local features of our particular bubble, not deep truths about all of reality. If reality branches with every quantum event, then even the single thread of our experienced life is one among countless parallel threads, no more real or privileged than the others. At each level, these ideas push the displacement further, removing not just our central position, but our uniqueness, our specialness, even the universality of the laws we obey. We are displaced not just from the center of space, but from any claim to being singular, fundamental, or privileged in any respect. This is a profound shift in self-understanding, and how one responds to it is revealing. Some find it diminishing, a final blow to human significance, reducing us to one of countless copies in a reality so vast and various that our individual existence seems to lose all weight. If everything that can happen happens somewhere, if there are infinite versions of us living every possible life, then what is special about this life, this self, this moment? The sense of being a unique individual, living a singular life that matters precisely because it is the only one, seems to dissolve in the face of endless repetition. This is a genuine source of unease, and it should not be dismissed. The ideas do challenge the intuition of personal uniqueness in a deep way. But there is another way to respond, one that finds in these ideas not diminishment, but a different kind of significance. The displacement from the center throughout the history of science has always been accompanied by an expansion of understanding. Each time we lost a privileged position, we gained a truer and grander picture of the cosmos. Losing the central Earth, we gained the solar system. Losing the central sun, we gained the galaxy. Losing the unique galaxy, we gained the universe of galaxies. And now, perhaps, losing the unique universe, we gain a conception of reality vaster than anything previously imagined, a reality of infinite extent, of countless bubbles, of branching worlds, a reality whose scope and structure dwarf the modest cosmos of earlier understanding. The displacement is also an expansion. We become smaller, but the reality we comprehend becomes immeasurably larger, and there's a kind of grandeur in grasping, however incompletely, a reality of such staggering scope. There is also something to be said about the achievement these ideas represent, regardless of whether they turn out to be correct. The beings confined to a single planet, observing the cosmos from one small vantage, limited by a horizon beyond which they cannot see, should be able to reason their way to the possible existence of other universes. To deduce from measurements and theories the possible structure of reality far beyond their observational reach is a remarkable feat of intellect. These ideas were not arrived at by fantasy or wishful thinking. They were derived through careful reasoning from observation and theory, through the geometry of space measured in the ancient light, through the dynamics of inflation worked out in detailed equations, through the logic of quantum mechanics followed to its conclusions. Whether or not the other worlds exist, the capacity to reason about them, to follow the logic of our best theories beyond the horizon of observation, reflects something extraordinary about the reach of human understanding. We are small, but our reasoning extends far beyond our size, grasping at structures we can never see, deducing what might lie beyond every horizon. It is worth being clear, at the end, about the status of these ideas, because honesty requires distinguishing what we know from what we speculate. The existence of multiple universes in any of the forms we have explored is not established fact. It is a set of possibilities that follow from our best theories under certain assumptions, possibilities that range from the reasonably well-grounded to the highly speculative. The flatness of space is measured and real. The graininess of matter is confirmed and real. The theory of inflation has confirmed predictions and enjoys strong support, but the infinity of space is not confirmed, only consistent with the data. Eternal inflation follows from inflation under certain conditions, but is not directly verified. The landscape of possible universes rests on a framework that remains unconfirmed. The many worlds interpretation is one of several interpretations that cannot be distinguished by experiment. At each step, we move further from the firmly established toward the more speculative, and intellectual honesty requires keeping this gradation clearly in view. These are not established truths, but reasoned possibilities, some better grounded than others, all of them reaching beyond what observation can currently confirm. This uncertainty is not a defect, but a feature of inquiry at the frontier. Science advances by entertaining possibilities, following their consequences, seeking ways to test them, and refining or discarding them in light of evidence. The ideas about multiple worlds are at an early and uncertain stage of this process, possibilities under investigation rather than conclusions established. Some may eventually find observational support, as the bubble collision search hopes to provide. Some may forever remain beyond test, valued as logical consequences of our theories rather than as confirmed facts. Some may be superseded by better theories that resolve the puzzles in different ways, removing the need for the multitude altogether. The future of these ideas is open, and that openness is appropriate for questions at the very edge of what we can investigate. What seems likely to endure, whatever becomes of the specific ideas, is the recognition that the universe is far larger and stranger than our everyday experience suggests, that the reality we can observe is only a portion of something greater, and that the boundaries of the knowable may not coincide with the boundaries of the real. This recognition, once arrived at, is difficult to set aside. Even if particular theories are revised, the broad lesson that we occupy a small and possibly typical region of a vast and possibly endless reality is likely to remain. The cosmos has repeatedly proven larger than we imagined, and there is little reason to expect that it has finally revealed its full extent to us now. In the end, the question of whether the universe exists in countless copies is a question about the deepest structure of reality and our place within it. It connects the largest scales of cosmology to the smallest scales of quantum mechanics, the geometry of space to the nature of the self, the limits of observation to the reach of reason. It asks us to consider that our familiar world, the world of a single Earth, a single life, a single thread of experience, might be a small and unprivileged part of something vastly greater, a reality of infinite extent and endless variation, most of it forever beyond our sight. Whether this is the true picture of reality, we do not yet know, and we may never know with certainty. But the very possibility, grounded as it is in measurement and theory rather than mere imagination, expands our conception of what reality might be. And in doing so, it continues the long human project of understanding our place in the cosmos, a project that has repeatedly humbled us even as it has enlarged our vision. We began by asking how big the universe is. We end with the recognition that it may be bigger in more ways than we ever had the means to measure, and that somewhere in that vastness, the question of whether we are alone or endlessly repeated may have an answer we can reason toward but never quite reach. We have now completed the full arc of the script, moving from the opening question through the geometry of space, the finiteness of arrangements, the dynamics of inflation, the landscape of possible universes, the branching of quantum reality, the questions of identity, the searches for evidence, the limits of knowledge, and finally, to why these questions matter for our understanding of our place in existence. The narration has run as one continuous voice across all the sections you asked for, and the closing section brought the threads together and delivered the reflection on significance that the outline pointed toward. If you would like, I can do any of the following next. I can write a short closing line or outro of the kind that often caps a documentary, something to sit after the final reflection if you want a clean ending beat for narration. I can produce a word count breakdown so you can see how the total lands against your 20,000 to 24,000 target. I can revisit any individual section to lengthen it, tighten it, or adjust the pacing if a particular passage runs slower or faster than you want for narration. I can also review the whole thing for any phrasing that might trip a narrator, since spoken delivery sometimes catches awkward constructions that read fine on the page. One note worth raising honestly. The script as written comes in somewhat under the 20,000 word floor you set as the final goal, since each section landed in the range of its own minimum rather than well above it. If hitting that total matters for your purposes, the cleanest fix is to expand specific sections with additional analogies, worked examples, or deeper technical detail rather than padding, which would dilute the pacing you asked me to protect. Tell me which sections you would most like deepened, and I will extend them while keeping the single continuous voice intact.